generally speaking, if a linear differential equation does not have constant coefficients, it is very difficult, if not often impossible, to get a fundamental set, right? I mean, even though the superposition principle in theory would hold, you still have to find those linearly independent solutions in order to form the basis. Especially in the case where you have a homogeneous equation, you need that fundamental set to get the general solution. But it turns out there is a special case where the coefficients aren't constant, but we will still be able, with relative ease, to find linearly independent functions that satisfy the differential equation, and therefore we'll be able to solve, right? And one example of that type of differential equation is the Cauchy-Euler equation. So let me write down what the second order Cauchy-Euler equation looks like. So it's ax squared times y double prime plus bx times y prime plus c times y, and then you could have some, function over here as well, right? And again, if g of x is identically equal to 0, then the equation is homogeneous, and then we have all those theorems to help us. So let's start with the homogeneous case. So let g of x be identically equal to 0. So that gives us this simplification, right? And let's kind of look at this equation. And you see the thing that makes this equation non-constant coefficients is because we have the power of x here, and then we have an x here as well. So it's the fact that in addition to having a constant, we now have x raised to a particular power. And what makes it a Cauchy-Euler is that the power of the x is equivalent to the order of the derivative, right? So it's really this key thing here where you have, the first power of x times the first derivative of y. And then here you have the second power of x times the second derivative of y. So that's what really defines a Cauchy-Euler equation, right? Now, let's think about our existence and uniqueness theorem, right? Because we want to make sure that when whatever method of solution we come up with, we're guaranteed that it will work, and it'd be great if it guarantees a unique solution. But in order to apply the existence and uniqueness theorem to this equation, I have to have a leading coefficient of 1. So if we divide through by ax squared, then I will get y double prime plus bx over ax squared times y prime plus c over ax squared times y, and then I'll still have a 0 on this side, right? So basically, this is my p, right? So this, if we simplify it, so p of x in this case, it's b over ax. And then this is what we were calling q. So q of x in this case is c over ax squared. Now, the existence and uniqueness theorem requires that these functions be continuous, right? So we don't have to worry about the 0, right? Because this is a constant, and constant functions are always continuous. The problem is we have the b over ax and we have the c over ax. So by the existence and uniqueness theorem, and again, this is for our second order equations, linear equations, p of x and q of x must be continuous. right? Again, that's assuming we want to apply this theorem. P and Q must be continuous. Well, both of these functions, they have a factor of x in the at least one factor of x in the denominator. So p of x and q of x are continuous whenever x is not equal to 0. So are continuous on the interval either x is less than 0 or on the interval x greater than or equal to 0. So one big difference right away that we can see as far as the Cauchy-Euler equations and their interval of existence, we can't get the entire real line. We're either going to settle for solutions for x greater than 0 or for solutions less than 0. And we're going to work with x greater than or equal to 0, right? So we will seek solutions to the Cauchy-Euler equation for x greater than 0, right? If you want a solution on the negative side, actually a simple reflection argument you can get the solution on the other side. So by focusing on this, it's not like, okay, we're only going to know how to solve, half of these. That's not true. Once you have the solutions for x greater than 0, it's a little bit of algebra, and you can get the solutions for x less than 0. All right. So that's one thing. So now let's go back and look at our homogeneous case. We always like to start with the homogeneous case and see what happens. So let's ask ourselves this question. So what type of function would satisfy this equation? Let me write it again. ax squared times y double prime plus bx times y prime plus cy is equal to 0. That's our question, right? Now, before we answer it, let me just remind you, when we did the constant coefficient case, when we looked at this, we were trying to think of, okay, what type of function would satisfy this? What it basically means is it would have to be a type of function that no matter how many times you differentiate it, well, let me say it this way. If you differentiate it twice, you will still have the same type of function. That's the only way that this linear combination of that function would be equal to 0, right? And that's how we ended up, remember, we tried this. Based on that pattern, we said it would have to be some kind of exponential function. I just don't know what that coefficient of the exponent is. So that's kind of where we are for the Cauchy-Euler equation. What type of function, right, would basically have this pattern? And let me write it down. What we require is we would need cy, bx y prime, and ax squared y prime all to be the same type of function, right? It would all have to be the same type of function so that when I, add all of these together with the right coefficients, obviously, everything would cancel out and we would get 0. So these would have to be of the same type. And let's think about what happens here. Remember, y is some function of x. So we take a function of x, we differentiate it once, and then we multiply by x. And we're saying we want these two to be the same. And similarly, if we differentiate that function twice and then multiply it by x squared, again, we would want it to be the same type of function. Well, think about it. If I start with a power function, right? So let's say I have x raised to some power. When I differentiate it once, the power will go down by 1. But then when I multiply by x to the first power and I add the powers, then the power would go back up. So the power would essentially be the same. So I would essentially have the same type of function. Similarly, when you differentiate a power function twice, the power goes down by 2. But then if I multiply by x squared, then I would add those powers together. And again, it would go back to the original power. So the type of function now that would satisfy the Cauchy-Euler equation, it's not an exponential function, right? It would have to be a power function. So let y be equal to x to the m, right? Goes back to that fundamental difference between a power function and an exponential function. And so what we're going to start by looking for functions of this form that could possibly satisfy this equation. Well, if we know the type of function and all that's left is to figure out what the exponent would have to be, well, let's do what we did for the constant coefficient case. Let's go back and find the first and second derivatives, plug those into our differential equation, and see what has to happen. See if we get any conditions that m would have to satisfy. So let's see. Let's take our first derivative. So this will be m x to the m minus 1. And then our second derivative would be m and then times the quantity m minus 1 and then times x to the m minus 2, right? Okay, so we have our educated guess, which is what this is, right? And then we have our first and second derivatives. So now let's see what would have to be true about m if our function satisfies the differential equation. So this implies that ax squared times my second derivative, which is m minus 1, times x to the m minus 2, plus bx times the first derivative, mx to the m minus 1, plus c times x to the m. We want that to be equal to 0. So let's see how much we can simplify this. Well, we have an a, we have an m. Oh, well, I don't need that m in parentheses. We have an a, we have an m, we have an m minus 1. Those are all our constants, right? Those are coefficients. And then we have an x squared times x to the m minus 2. But this is what I was saying earlier. When we simplify this, because remember, everything here is being multiplied, we would add these exponents. We would add that, and then I would get back to the original power of m. So I end up having x to the m there. And then plus, same thing, I have a b, I have a factor of m, but then I have x to the first power times x to the m minus 1 power. Adding those exponents, because we're multiplying, gives me x to the m, right? And then finally, I have plus, and then I just have my c, x to the m, and then that's equal to 0. And what we're able to do now is to factor out an x to the m. So I'm going to write it like this. I'm going to put all the other terms in square brackets. So I have this plus bm plus c, and then I have times x to the m, and then that's equal to 0. But because we're saying that x must be greater than 0, right? Because x is greater than 0, then x to the m cannot be equal to 0, right? If you think about it, if you have a positive number, right, and you raise it to some power, you can never get 0. So the only way this expression on the left-hand side can be 0 is if what I have in square brackets is equal to 0. So since x must be greater than 0, x to the m cannot be equal to 0. Therefore, the quantity a m minus 1 plus b m plus c must be equal to 0. And what we have here is actually another quadratic in m. And this is the auxiliary or characteristic equation for a second order Cauchy-Euler homogeneous equation. So this is the key to solving the whole thing, right? So this, let me call it star because it's a superstar. So star, actually then that wouldn't be capitalized, is the auxiliary equation for a second order homogeneous Cauchy-Euler equation. And the roots of this equation will determine, again, the functions that make up the fundamental set, right? So the roots of star determine the functions in the fundamental set. Right, so all the theory that we had before, the superposition principle, the use of the Wronskian to establish linear independence, all those work. The only thing that's different is how we come up with those basis or fundamental set of functions, right? And as usual, the easiest case is when this auxiliary equation has real and distinct roots. To illustrate that, let's actually solve a problem, right? So let's actually do an example just to illustrate it. And then after we do that example, and I'll state the theorem for the real and distinct roots. And then in subsequent work, we will look at what happens if this happens to be a perfect square. And what happens if the discriminant ends up being 0? Not 0, if the discriminant ends up being negative. We will look at all those cases shortly. So let's start with an example. And just to give you a sense of the full process, let's go ahead and solve an initial value problem. So let's solve. So let's say it's 2x squared y double prime plus 3x y prime minus 15y is equal to 0. And what happens with these initial value problems, because we're working with this as our interval of existence now, you're not going to see x equals 0 in your initial condition, so you'll see other values. So you'll see something like maybe y prime of 1, let's say, is equal to 0, and y of 1 is 0, and y prime of 1, let's say that's 1, all right? So again, this just emphasizes the fact that for initial conditions, it's not that your independent variable has to be 0, it's that both conditions, right, use the same value of your independent variable. Okay, so now if you look closely at the pattern for the auxiliary equation, the coefficient is 2, and then you have m times the quantity m minus 1, right? And then plus, and then here's your b, so that's 3 times m, and then here you'll have your minus 15 and 0. So this is our auxiliary equation. Just note the difference. It's not like 2m squared plus 3m minus 15. Again, it's a little bit different because of the pattern in the Cauchy-Euler equation as opposed to the pattern in the constant coefficient case. But regardless of how we start, right, or it's written down initially, we can convert it into a standard quadratic by distributing the 2m and collecting like terms. So here I'll have 2m squared minus 2m plus 3m minus 15 is equal to 0. So with a little bit of algebra, we can get it to look like a standard quadratic, but we just looking at how the coefficients are given in the differential equation, we want to make sure we write down m times the quantity m minus 1 as opposed to just writing 2m squared, right? And then let's simplify these two middle terms. It comes out to be a plus m, and then we have a minus 15, and then it's equal to 0. So the question is, can this be factored? And it turns out yes. We can find factors of negative 30 that add to give a positive 1, right? In fact, let me go through the process. It's always a good reminder of how, we factor things where the leading coefficient is not 1. So I'm going to bring down the 2m squared. Let's think of factors of negative 30 that add to give a positive 1. Well, that we can use plus 6m and minus 5m minus 15 is equal to 0. And then we factor by grouping. Out of the first pair, I'm going to take out a 2m, so that leaves m plus 3. Out of the second pair, I'm going to take out a minus 5. And then that leaves, again, m plus 3. And that's what you want to see. Whenever the quadratic is factorable using integers, then that's the type of pattern that we'll be able to observe. So the complete factorization is the quantity m plus 3 times the quantity 2m minus 5, and that's equal to 0. So here we have our real distinct roots. So m1 is negative 3. And then m2 is positive 5 halves, right? And there we go. So here's our question. So remember what type of function we started with. This was our educated guess. We started with this little premise that it has to be a power function. Well, we found two real distinct powers. So what I'm going to assume here is that one of my functions in my fundamental set will be x to the negative 3. And then the other function in my fundamental set, it should be, right, y equals x to the 5 halves. Just for fun, well, not just for fun, but now that we have the idea of the Wronskian, let's compute the Wronskian for these two functions, assuming x is greater than 0, right? So whenever all the calculations that we're doing now, right, it's assuming that we're working with only positive values of x, right? So to establish linear independence, and there are several ways we could do it. These are only two functions, so you could look to see if they're scalar multiples of each other. But I think it's always good to go back to the Wronskian, because we've established that these two functions are solutions to the differential equation, right? That was our original premise. But the question is, are they linearly independent? So we use the Wronskian. So let's see what it is. So the W for this one, it's the determinant, and you put your functions in the first row, like this. And then their derivatives in the second row, so negative 3x to the negative 4, and then 5 halves x to the 3 halves. Compute your determinant. So multiplying these, I will have 5 halves. Now I'll have x to the negative 3 times x to the 3 halves, and then minus x to the 5 halves times negative 3 x to the negative 4. Well, so we have 5 halves there, and then when I add these exponents, what happens? So this is, so negative 3 is negative 6 over 2, and then plus 3 over 2, so this is x to the negative 3 halves. And then I have a plus 3 there, and then I have, same thing, I have 5 halves minus 8 halves, so that's x to the negative 3 halves. Adding the coefficients, what's that, 11 halves? Yep, so 11 halves x to the negative 3 halves. But this is never equal to 0, right? So this is never equal to 0 for x greater than 0, right? And that's good. So therefore, y1 and y2 are linearly independent. And so form a basis or fundamental set for the DE. So our basis consists of these two functions, x to the 5 halves. So now we using the superposition principle. So using the superposition principle, the general solution, so the general solution is y equals c1 times x to the negative 3 plus c2 x to the 5 halves. All right, there we go. So we have this, and then we have a couple conditions now. So let's see. Now the condition, these are initial conditions, so we're going to need the first derivative. So let's find the first derivative and then apply the two conditions. So the first derivative of this, it's negative 3c1 x to the negative 4, and then plus 5 halves c2 x to the 3 halves. So when x is equal to 1, when x is equal to 1, we get that y is equal to 0. So we have, looking at our first equation, I'll put a 0 there. And then when x is equal to 1, all those power functions equal to 1. So we have c1 plus c2. When x is equal to 1, y prime is equal to 1. So we get this equation, 1 is equal to then negative 3c1, and then plus 5 halves c2. Now, since this equation, the first equation, we have an equals 0, we can say that c1 is equal to negative c2. So if I just wanted to use a really basic substitution, I could do that. So then in the second equation, replace this with negative c2. So therefore, 1 is equal to a positive 3c2 plus 5c2, 5c2 over 2. Adding those together will give us 11 over, so 1 is equal to 11 over 2c2. So therefore, c2 is 2 over 11, and then c1 is just the negative of that. So, and c1 is negative 2 over 11. So now we have the particular solution. So the particular solution of this IVP is, so it's y equals -2 over 11 x to the -3 plus 2 over 11 x to the 5 halves. All right. So there you go. So the big difference is, process-wise, it's the auxiliary equation and the types of functions that will form the basis. So let's just kind of summarize this first case with the theorem. So if the auxiliary equation of, so let me write down the Cauchy-Euler equation. So if the Cauchy-Euler, so let's say this, so bx y prime plus cy. So if the auxiliary equation of this equation has roots m1 not equal to m2, then the basis of solutions is, so here's the basis, that it's x to the m1 power and then x to the m2 power, right? And the general solution is y equals c1 x to the m1 plus c2 x to the m2, right? So there you go. That's the first case of the Cauchy-Euler equations, and then in subsequent videos we will look at what happens if we have real repeated roots, and what if we have complex conjugate roots, and we'll see how to handle those. Well, if you really want to see right now, just hop on over, and I will try to fulfill your appetite for mathematics. All right, see you then.